In this video, we're going to talk about two different subsets of Rn. One of them are called open subsets, and the other one is closed subsets of Rn. So what are open subsets of Rn? A subset of Rn is called open if any point in that set, for any point in that set, there's an open ball around it that is completely contained in this set. So if you look at something like this, a set like that, excluding its boundary, if you take any point inside, then there's a ball around it that is contained completely inside this set. Or if you look at perhaps like a half plane, the portion of the plane to the right of a line, a vertical line, this would be an open set, and the reason is if you take any point in that set, there's a ball around it that is completely inside that set. So let's look at an example and formally, in fact, prove something is open. For any positive number r and any a in Rn, the ball centered at a with radius r is an open subset of Rn. And this is in fact the reason we call this an open ball. Okay, so in order to show this is open, we will have to show that any point that we take inside this set, so this is the open ball, it excludes its boundary. If I take something in here, there is a ball around it that is completely inside this original ball, and the center here is A. Now we'll have to find the radius of this ball and argue that in fact the ball is completely within the original ball. Okay, so how do we find the radius of this ball? Well, the closest point to B that is on the boundary of this disk, this I'm looking at a two-dimensional case, is this point right here. So if you look at like a tangent circle, the distance is going to be the difference of radius and the distance from B to A. So in other words, I'll have to take the radius to be something less than radius, which is r, minus B minus A. So let B be in the ball of radius r centered at A. Now by assumption, or by definition, of ball of radius r centered at A, the distance between B and A is less than r. So now let S be r minus the radius, the distance between B and A. So we will show that ball of radius S centered at B is inside ball of radius r centered at A. So we'll take something of distance less than S, and then we'll have to show this distance is less than r. So we know something about this distance. This is B minus A. So how do we compare these with triangle inequality? So we start with let x be in the ball of radius S centered at B. So by definition of ball, the distance between x and B is less than S. Now if you look at the distance between x and B, that's less than r plus r minus B minus A, because that's what S is. Now we are trying to show that x is in fact in the right hand side, in the ball of radius r centered at A. So how do we do that? We'll have to take the distance between x and A and show that this distance is less than r. So we know that this distance is going to be less than or equal to the distance between x and B plus the distance between B and A. Now we'll have to use the assumption, what we found up here. This is less than, so the distance between x and B is less than r minus norm of B minus A. This is distance between x minus B is less than that, which is coming from here, and then plus the distance between B and A. And then clearly these two cancel, so we get the distance between x and A is less than r, which means x is in fact in the ball of radius r centered at A. So what we showed was if you start from something in the ball of radius S centered at B. It is in the ball of radius R centered at A. Therefore, we showed the inclusion. Therefore, ball centered at B of radius S is inside the ball centered at A of radius R. And of course, these are all both open balls. So now by definition of open sets, ball of radius R centered at A is an open subset of Rn. Okay, so this is the first example of an open set. Okay, so one very important property of open sets is that if you take a look at the empty set, that's open. Rn is also open. The union of any collection of open sets is open. So if you take a bunch of open sets, they don't have to be finitely many. They could be infinitely many, they could be countable, or they could be uncountable. Then the union would also be open. Intersection of any finitely many open sets is also open. Okay, so let's look at the empty set. Empty set is open. This is just really like a logical statement. So what does that mean? We need to show this. We need to show if X is in the empty set, then there is an open ball centered at X that is contained in the empty set. Okay, but if we look at this, if this is always false. So in math, if then statements, if the assumption is false, the whole statement is true. So this is true. Therefore, the empty set is in fact open. Okay, so that tells us that the empty set is open. Now, what about Rn? So let's start from something in Rn. Then, if you take any ball centered at X, this is completely inside Rn, because everything is in Rn. Every element of Rn is in Rn. So this is by definition of ball. And that means Rn is in fact open. So that's for the first part of this theorem. The second part tells us that the union of any collection of open sets is open. So let's look at a collection of open sets and then show that the union is open. So suppose Ui, where I is in I, is a collection of open subsets of Rn. We would like to show that the union of Ui's are all open. So how do we do that? We will take an element inside the union, and then we'll have to show that there is a ball around it that is completely inside the union. So let X be in the union I in I of Ui. Now, by definition of union, X is going to be in one of these sets. X is in Uj for some j in I. Now, I know that Uj is open. So since Uj is open, there is some radius positive such that ball of radius R centered at X is completely inside Uj. But if something is inside Uj, it would be in the union of Ui's as well. That's by definition of union. So by definition of union and subset, ball of radius R centered at X is in fact inside the union of all the Ui's, I in I. And what does that mean? It means for every point inside the union, we found a ball around it that is completely inside the union. Thus, the union of Ui is in fact open. So union of any collection of open sets is also open. Next one is for finite. So we have the intersection of any finitely many sets, open sets is open. So for finite, we can't really take infinitely many sets. We'll have to take finitely many. So let u1 through un be, or um, be open subsets of Rn. So we're going to take an element in here. So let x be in the intersection of ui, I equals 1 to m. And we are going to show that in fact there's a ball around it that is inside all of the ui's. Now we know that there's a ball around that point x that is inside u1, and there's a ball around it that is inside u2, and so on. So we're going to take these balls. There's a ball around x that is inside u1, there's a ball around it that is inside u2, there's another ball that is inside u3, and so on. So we're going to take the smallest of these radii that would be inside all of them. So by definition of intersection, x is inside ui for I equals 1 through m. So what does that mean? It means, so since ui is open, there is some radius positive, so let's say ri, such that ball of radius ri centered at x is inside ui for I equals 1 to m. Now we're going to take the smallest of these radii and we're going to call that r. So let r be the minimum of r1 through rm, which is in fact positive because we're taking the minimum of a bunch of positive numbers. If y is inside the ball of radius r centered at x, then the distance between y and x is in fact less than r, because that's by definition of ball. By definition of the ball of radius r centered at x. So now r is the smallest of the ri's. So since r is less than or equal to ri, the distance between y and x is in fact less than ri for every I, for I equals 1 to m. What does that mean? It means in fact x is y is in fact in the ball of radius ri centered at x, which we knew it was inside ui. And what does that tell us? It tells us y is inside ui for all I equals 1 through m. Therefore, so we showed that y is inside ui for every I. What does that mean? It means it's in the intersection. So y is in fact in the intersection of ui, I equals 1 to m, by definition of intersection. So now what did we show? We showed that if we take something in the intersection, then ball of radius r centered at x is centered at y, centered at x is in the intersection. So let's go back and look at what we did. I believe it's x. So here's what we did. We took an element inside ball of radius r centered at x, and then we showed that this element is in the union, is in the intersection. What does that mean? It means this set is in fact a subset of the intersection. And therefore, by definition of open sets, by definition of open sets, intersection of ui, I equals 1 to m, is in fact open. What we showed was that if you take a bunch of open sets, the intersection is in fact open. So very important that we are looking at finitely many sets. In fact, we are looking at an example that tells us why we cannot guarantee the intersection of infinitely many sets, open sets to be open. So by an example, show that the intersection of a collection of open subsets of Rn may not be open. So the trick here is to create sets that we can't take the minimum here. We took the minimum of our i's, but the minimum could get could basically become 0 if you have infinitely many of these. So here is now what we're going to do. So let ui or un to be the interval from -1/n to 1/n inside R. Okay, so first of all, un is ball of radius 1/n centered at 0 by definition. Okay, now by an exercise or by an example that we just did earlier, by an example, -1/n to 1/n is open because it's a ball. Every open ball is open, so therefore this open ball is in fact open. Now we're going to show that the intersection contains only the singleton 0. Now we claim that the intersection of -1/n to 1/n, n equals 1 to infinity, contains only the 0, the number 0. Okay, so how do we show that? Let's assume that x is in the intersection. So what does that mean? It means x is between -1/n and 1/n. So if it were positive, it would be more than some 1/n because 1/n approaches 0. And if it were negative, then it would also be more than some -1/n, less than some -1/n. So that is a contradiction. So if x were positive, then there would be a positive integer m such that x is more than 1/m. And that tells you that x is not in the interval -1/m to 1/m. And if x were negative, then negative x would be more than 1/m for some positive integer m, which means x would be less than -1/m, which means x is not in the interval -1/m to 1/n. So what does that mean? It means nothing positive is in the intersection, nothing negative is also in the intersection. Therefore, x must be 0. If x is in the intersection, then x cannot be positive, x cannot be negative, therefore x is 0. On the other hand, 0 is in the intersection. So 0 is in the interval from -1/n to 1/n for all n. And that means the intersection is in fact a singleton. So this intersection is in fact a singleton 0 and goes from 1 to infinity. Okay, so now we're going to show that this set is in fact not open. So we will show this set is not open. So let's take let's assume on the contrary that this is open. So assume on the contrary this set is open. So what does that mean? Therefore there would have to be, therefore there is some radius positive such that ball of radius r centered at 0 is contained inside this set. So what does that mean? It means the interval from negative r to r is completely within the interval, the singleton 0. But that doesn't make sense, because if you look at some positive number here that cannot be inside the singleton 0, for example, r over 2 is not in this set, and r over 2 is in that set. So this is a contradiction. So what does this mean? Therefore, this is not open. So bottom line is the intervals from negative 1 over n to 1 over n, they're all open, but their intersection is not open. Okay, so next we're going to look at closed sets. Closed sets are complements of open sets. So a subset of Rn is said to be closed if Rn minus a is open. Okay, so here's an example. Prove that the intervals, closed interval from a to b, open negative infinity to closed b, and closed a to open infinity, they are all closed subsets of R. Okay, so in order to see if that they are all closed, we'll have to look at their complement. So look at the complement of the first one. So this is every real number that is not between a and b. So that means it's either less than a or it is more than b. We will show that each one of these is open. So we will show negative infinity to a is in fact open. So how do we show something is open? We will take, let me draw a diagram here. So this is a. We will take something in here, let's say x, and we want to show that there is a ball around it that is completely inside the set. So we cannot go beyond a. So we have to take a radius that is less than or equal to a minus x. So let x be in the interval negative a to a. So that tells us x is less than a. Set the radius to be a minus x, which is positive because a is more than x. Now we claim that ball of radius r centered at x is in fact inside negative infinity to a. So that's not very difficult to see. Let's take something in the ball of radius r centered at x. So that tells us y minus x must be less than r, which means y minus x must be less than r, which is a minus x, and more than negative r, which is a minus x. Now we don't actually need the left side inequality. The right side tells us y is less than a, which means y is in the interval negative infinity to a. So we showed that if you have an element in the ball, then it would be in the interval. So that tells us the ball of radius r centered at x is in fact inside negative infinity to a. Now we showed that every point inside the interval negative infinity to a, for every point inside that interval, there is a ball around it that is completely inside that interval. Therefore, interval from negative infinity to a is in fact open. And that completes the proof of the fact that this is open. Now we will have to show the other one is also open. So similarly, and I won't write down the details of this one, similarly the interval from b to infinity is open. Now so this is something that needs to be done. By a theorem, their union negative infinity to a union b to infinity is open. And by definition of closed, the complement of this one is closed. So by definition of closed sets, the complement, which is the closed interval from a to b, is in fact closed. Now for the other one, we basically have shown what we wanted. So we know that interval from negative infinity to Let's see, what do we have? So the complement of this one is negative infinity to a. We know this is open, thus a to infinity is closed by definition of closed sets. And finally, the last part would be very similar again, because we know the interval from b to infinity is open. The interval from negative infinity to a to b is in fact closed. Yeah, I guess I don't need like a thus here, but in any case. Okay, so this is closed by definition of closed sets, and that completes the solution. Okay, so now if you look at the definition that we just talked about of closed sets are defined based on open sets. Now the question is, can we come up with a standalone definition for closed sets without having to rely on the definition of open sets? And this theorem in fact gives us the answer to that. It tells us that a subset of Rn is closed if and only if it contains all of its limit points. And to just remind you, a limit point was a point that every ball around it contains a point of the set that is not the center. So this is if and only if, which means it is a very good theorem, and anytime you want to prove something is closed, you could potentially use this theorem as well. Okay, so first direction is, we know it is a subset A is closed. We want to show that it contains all of its limit points. So suppose A as a subset of Rn is closed. We'll have to show that it is it contains all of its limit points. So let x in Rn be a limit point of A. Okay, so what do we need to show? We need to show that x is in fact in A. So suppose on the contrary, x isn't in A, but we know that A is closed, which means by definition of closed sets, the complement Rn minus A is open. But what we know is that x is in Rn minus A. So since x is in Rn minus A, there is a ball around it, there is R positive, such that ball of radius R centered at x is completely inside Rn minus A. So what does that mean? It means there is nothing inside ball of radius R centered at x and A. That tells us ball of radius R centered at x does not intersect A. And this violates the fact that x is a limit point. X is not a limit point. This is just by definition of limit points. Because limit point was a point that any ball around it does intersect A at a point other than x. This doesn't intersect A at all. Okay, so the second direction. We know that A contains all of its limit points, and we want to show it is in fact closed. So suppose A contains all of its limit points. We want to show A is closed. So in order to show A is closed, we'll have to show the complement is open. So we need to show Rn minus A is open. So how do we show something is open? We'll have to take a point inside this set and we'll have to find a ball centered at that point that is completely inside the complement. So let X be something in that complement. Okay, so what we know is that A contains all of its limit points. Since A contains all of its limit points, X cannot be a limit point of A. X is not a limit point of A. Why? Because, well, X isn't in A. So it cannot be a limit point because A contains all of its limit points. Now that we know it is not a limit point, by definition, there is a ball around it. There is R positive such that ball of radius R centered at X intersection with A minus X is in fact empty. So there is no element inside ball and A minus X. But A doesn't contain X. So X is not in A. So that means A minus X is just A. So what does that mean? Therefore, ball of radius R centered at X and A are disjoint. There's nothing in common. So what does that tell us? It means ball of radius R centered at X is outside of A, is inside Rn minus A. What did we show? We showed that if you take an element inside Rn minus A, there is a ball around it that is completely inside Rn minus A. So this, by definition of open sets, Rn minus A is just open. So what does that tell us? Now, by definition of closed sets, A is closed. And that's exactly what we wanted to show. We wanted to show if A contains all of its limit points, then it would be a closed subset of Rn. And we already showed the other direction. Okay, finally, for the last thing in this video, we're going to go over some properties of closed sets. So this is kind of the mirror image of what we did for open sets. The empty set and Rn are both closed. So, well, if you look at Rn minus empty set, that's just Rn. So this is open because of the previous theorem. So that means the empty set is closed. If you look at Rn minus Rn, this is the empty set, which is open. And that tells us that Rn is closed. Now we have to show that the union of any finite number of closed sets is closed. So that's part B. So let C1 through Cm be closed subsets of Rn. Now we'll have to take the union of these and we'll have to look at the complement of these. So Rn minus the union of Ci, I equals 1 to m. This is basically the complement inside Rn. This is union of Ci complement. Now, by De Morgan's law, this is equal to the intersection of Ci complement, I equals 1 to m. Now, by definition, which is just basically intersection is just like Rn minus, complement is just Rn minus Ci. Now, by definition of closed sets, Rn minus Ci is open. Now we had a theorem that intersection of finitely many open is open. By a theorem, intersection of Rn minus Ci is open. I equals 1 to m. Now we showed that this intersection, this intersection is open, which means this is open, which means the union of Ci's is in fact closed. So that tells us that Rn minus the union of Ci, I equals 1 to m, is in fact open. And what does that mean? It means the union of CI's is closed by definition of closed sets. Okay, so that's the second part. The third part is quite similar. So the third part tells us the intersection of any collection of closed sets is closed. So quite similar. So suppose Ci I in I is a collection of closed subsets of Rn. Now we take the intersection, because they said intersection of any collection, and then we take the complement. So intersection of Ci complement I in I, and this complement is in Rn. This is equal to, by De Morgan's law, this is the union of Ci complement I in I. Now these are all open, so this is like the Rn minus Ci. These are all open, so by definition of closed sets, Rn minus Ci is open. Now by a theorem, union of these is also open. Rn minus Ci is open, which means the intersection complement is open, which means the intersection must be closed. So that tells us that the intersection of Ci I in I is in fact closed, and that's what we wanted to show. Okay, so next time we'll talk about the relation between functions and these open and closed sets. So I will see you in the next video.